Hello and welcome. Up to this point in the class, we've been talking about relatively simple ways of analyzing data, particularly finding differences in means across different groups, differences in proportions across different groups, and ways of testing for statistical significance in different ways depending on the kind of data that you have. In the next couple lectures, we're moving on to quantifying exactly how different variables are related to one another. This is going to broaden the types of questions that we can answer, the sorts of hypotheses that we can test, and things like that. So specifically, we're going to start by looking at bivariate relationships, so relationships between one dependent variable, our outcome or response variable, and one independent variable or explanatory variable. So this scatter plot represents data from each of the 50 states as well as Washington, D.C. in 2012 about two different variables. One of them is the percentage of high school graduates in all of those places, and the other is the percentage of residents who live below the poverty line in each of those places. So looking at this scatter plot, can we tell which variable is our response variable, our dependent variable? Which is our explanatory variable, our independent variable, and how would you characterize the relationship between these two things, the percentage of people living below the poverty line and the percentage of people who have graduated high school? Take a minute and see if you can answer those questions. So theoretically, we can imagine that the relationship between high school graduation and poverty could flow in both directions. So that is to say that it could be when there are more people living in poverty, there are also more people who are likely to drop out of high school early and not graduate and just start working. And it can also be the case that when there are fewer people who graduate high school, that those people end up earning less, which contributes to a higher poverty rate. So the theoretical relationship between these variables could go both ways, and in the real world it probably has a sort of a looping effect going on where both of those variables are affecting one another simultaneously. However, when we're looking at a scatter plot, we do have specific information about which variable is considered to be the response variable and which variable is considered to be the explanatory variable. The dependent variable, the outcome that we're interested in, is always plotted on the y-axis, the vertical axis, and the explanatory variable, the independent variable that we're interested in, is plotted on the x-axis, this horizontal axis. So based on the way that this data is plotted in the scatter plot, we can tell that the percentage of residents in poverty is our dependent variable, and the high school graduate rate is the independent variable. We can also see that these variables are negatively related to one another. So as the high school graduation rate increases, percentage in poverty decreases. As high school graduation rate decreases, percentage in poverty increases. So they have an inverse or negative relationship to one another. We can also see that this relationship seems to be more or less linear. You could draw a straight line through these data points and that would pretty well represent what this data looks like. And we can see that the relationship is pretty strong. It seems pretty clear how the data are trending and the shape of the relationship between those data points. So that's the relationship between these two variables in this scatter plot. Now, of course, it's not very precise or very useful to say something fuzzy like these two variables have some negative relationship to one another. That doesn't give us a whole lot of information about how those variables are related. So we're going to introduce in this lecture a more useful and precise concept called correlation. Now, you're probably familiar with the language of correlation. It's sort of used loosely to talk about the association between two variables. But we're going to talk about a particular, precise definition of this. Correlation is a measure that captures the strength of the linear relationship between two variables. It takes on values between -1 and +1. So a value of -1 indicates that there is a perfect negative correlation between two variables, and positive 1 indicates that there is a perfect positive correlation. So both -1 and positive 1 indicate that there is a deterministic relationship between these two variables. So if we know the value of one variable, we know exactly what the value of the other variable will be. That's what it means for them to be perfectly correlated. A value of 0 for the correlation coefficient means that there is no linear relationship between those variables. So we're not going to be calculating correlations by hand in this course, but just so you know, the most commonly used measure for linear correlation is this thing called the Pearson product moment correlation coefficient. And we're going to denote that with the letter R. So this measure is based on how two variables covary with one another. The formula for covariance is another complicated calculation, but it's the covariance between these variables x and y divided by the standard deviation of each of those multiplied together. And that's how this particular correlation measure is calculated. Now, we can calculate correlation really easily using software, particularly using R. And so we're not going to need to calculate correlation by hand, but just so you know, first of all, there are multiple ways of measuring correlation, and second, the most common way, the way that we're going to be talking about in this class, is this particular Pearson correlation coefficient. So let's work on building some intuition about correlation coefficients. Remember, correlation coefficients are between -1 and 1, where negative values equal negative correlation, and the closer that value is to -1, the closer it is to perfect negative correlation. Positive values indicate positive correlation, and the closer that value is to +1, the closer it is to a perfect positive correlation, and a value of 0 indicates that there's no linear relationship between those variables. So looking at this scatter plot, this is the data that we were just looking at, the relationship between poverty and high school graduation. How would you estimate this particular correlation? Well, we've already established that this is a negative relationship between these variables, so we can eliminate the options that have a positive correlation coefficient, so options A and D. We know that option E is wrong because correlation coefficients can't be less than -1 or greater than +1. And so we're left with the two plausible negative options, so B, -0.75, and C, -0.1. So these two coefficients differ quite a bit in how strong they think this relationship is. So C says that there's a pretty weak linear relationship, and option B, -0.75, indicates a pretty strong negative linear relationship. So the data points around this line are not too far from the line. You can see they follow a pretty clear pattern here. So the relationship isn't very weak. It doesn't look like there's close to no relationship between these variables. And so we're going to go ahead and conclude that option B is the most likely correlation between the poverty rate and the graduate rate. Now let's try this same exercise again with a different set of data, this time looking at the relationship between the percentage of people living below the poverty line and the percentage of single mother households in each state and Washington, D.C. So again, I've given you a list of possible options here. So go ahead and pause the video and see which coefficient you think is most likely for capturing this relationship. So we can see that these two variables have a positive relationship with one another, so we can eliminate the negative options out of this list. And then we're choosing between a really weak correlation of 0.1, a really strong correlation of 0.9, and sort of a medium correlation of 0.5. So a really strong positive correlation would have the data points really closely clustered around a positive sloping line, and a really weak correlation of 0.1 would be kind of difficult to ascertain just looking at a scatter plot. Those points would be pretty diffuse, would be hard to tell if there was a clear relationship between those variables. So our best option here is E, a correlation of 0.5. There's a distinguishable positive relationship between these variables, but it's not super strong. Looking at these four scatter plots, for which of these scatter plots is there the strongest correlation? So a correlation coefficient that's closest to +1 or -1. So this is actually a little bit of a trick question. It's really clear that in plot A, these two variables are really closely related to one another. The points are really closely clustered together around this curving line. But the key point here is that that line curves. So it's not a linear relationship between the explanatory and response variables. It is a nonlinear relationship. The relationship's got a curve in it. So the plot that has the strongest correlation is actually plot B. You can see that the relationship between those two variables in plot B is really strongly linear, and those points are really clustered together around that positive sloping line. So plot B has the strongest correlation. To conclude here, I think that this graphic is a really good summary of what we can learn from correlation coefficients. So looking at this top row here, we can see the difference between what a positive and negative correlation look like, what the different slopes of those correlations are, as well as the relationship between how tightly the data points are clustered around this line, and how large the correlation coefficient is. So in the middle, where we have just sort of this diffuse cloud of points and basically a circle, that's a correlation of 0. There's no clear linear relationship through that cloud. And then as we move out to either side, we can see more and more strong correlations. In the second row of this graph, this tells us something really important about correlation coefficients, which is that we can have lots of different slopes of these perfect correlations, but the correlation coefficient itself is only going to tell us how strongly those variables are related to one another, not what the slope of their relationship is. It can tell us if it's positive or negative, but that's it. And then finally in the bottom row here, we can see that there are all sorts of relationships, different shapes, for how these data can be related to one another that a correlation coefficient is not going to capture. So wavy, nonlinear relationships, a correlation coefficient isn't going to be able to capture, and all sorts of different shapes of these data clouds here, the correlation coefficient is not going to be able to tell us anything about. The correlation coefficient is only able to tell us about linear relationships, the strength of those linear relationships and whether they're positive or negative. It can't tell us about nonlinear relationships, and it can't tell us about the slope of linear relationships. So that's been our lecture on correlations. Thank you for tuning in. I'll see you next time.